Hope you're having a beautiful spring Friday, and hope it's going to be a productive one. So the title of our webinar today is How to Size Your Storage, refreshing our assumptions on how much is enough. So with a lot of new battery technologies hitting the market and increased popularity of some newer applications, we thought it'd be a good time to put some materials together and give you our thoughts on how we size systems, the recommendations we make to customers on not necessarily which storage, but how to think about how much you're going to need and what tools are going to fit the application. So as you know, I like to start with an agenda so we can be clear on where we're going. Just real quickly, why is this important to get right? Why do we spend so much time hemming and hawing over load details, et cetera? And then we'll talk some specifics on sizing for different applications, kind of where we've been historically, how we go about doing these things, what information we look to guide our judgment, and then where we're headed. And these are, specifically what I meant here was sizing for time of use self-supply, what are the considerations to make there, sizing for demand charges, peak load shaving, and then some time for some questions. So if you've been to our dealer conference, you've seen Brad talk, you've seen him do 2 full hours packed with how to do off-grid sizing. So we definitely won't be covering today any of these topics in that level of detail. This is meant to be kind of a refresher, a primer, a best practices, if you will. Obviously, if you've got any questions on this, feel free to reach out to myself, Brad. Use the tech@aesolar.com email alias, and we're more than happy to answer your questions in the right amount of detail for you. So that said, let's get kicked off here. Why is sizing so critical? I think there's 2 critical things we've got to think about when we're doing system and storage sizing, and 2 scenarios you really want to avoid. On the left side, under batteries. So what does this mean? Simply put, not enough storage for your application and your loads. And I think the worst case scenario here is your battery is too small. The system runs but does not perform well. And essentially, what's going to happen in most of these cases is the battery's just going to cycle too much. The battery is too small, so it's going to discharge, I guess, more quickly than optimal. You're going to end up cycling it. You're going to discharge it, charge it, discharge it, discharge it, charge it, and that's going to lead to early replacement. So that's kind of a rosy picture for a worst case scenario. I think the true worst case scenario is in not lining up your battery with your charge amps. You're going to kill the batteries very quickly, or possibly cause some bodily harm or some mechanical equipment failure. So none of those are good situations, and that's why I think typically we've as an industry tried to coach people to err on the high side of storage. The drawback there on the right side of this chart is if you're over batteried, so more storage than is required for that application, you may lose the job entirely. If you do win the job with that over batteried bill of materials, it's going to eat into your profit margin, in addition to being more complex, more difficult to design, et cetera. So all of this hopefully should be fodder for, boy, let's make sure we do this right. Let's make sure we really nail the numbers, and we've got a real tight proposal on what the customers told me and what I'm recommending for the job. So that said, I wanted to start with some real quick and easy thoughts on off-grid sizing. And as this is an industry that has come from this application, I think it's a great place to jump off of. So this is my quick and dirty explanation of off-grid sizing that I typically do in webinars and training classes, and then Brad's going to follow up with a lot more detail. But in off-grid sizing, typically the way I teach this to installers is you're going to look at your application and you're going to try to size your inverter first to your kW peak. So as you look at as you look at all your loads in a, in a home, in an RV, in a boat, in a cabin, wherever, you're obviously going to need to know a couple things. You're going to need to know what's the nameplate capacity for most of these loads, and we can help you with some swag on some things. You're not going to need to look up, every single light bulb, every single microwave. You're going to need to know, generally speaking, how many of which types of devices. The first number there you're going to need to kind of put together is to think about your peak KW number. So I refer to this as a coincident peak. What's the 95th percentile number for what your KW is going to be if all the loads are on at once. I say 95th percentile because I think it can be debilitating to think about a scenario where every single appliance or light is turned on in the customer's location. Use your best sense on what they're going to run concurrently. That's going to give you your KW number. That's going to size your inverters to know how much power do I need to support, kind of worst case scenario at any given time. What's the continuous current going to be, and what's the peak or surge current going to be. From there, we can figure out, okay, we know our peak number. We know by doing this load study what's our energy number going to look like in a given day. Typically we're talking about worst case scenario, so it's typically energy number for off grid in winter, because you're thinking worst case scenario in terms of insulation. And I think Brad had some points on this, but we're looking more and more at as air conditioning has got a lot more affordable and efficient. We're now looking at, you probably want to think about your summer number too. In any event, you're going to want to know your base case for energy. So that's going to dictate, how much storage do I need to be able to do 1 day of autonomy, or 2, or I guess in theory 3 days, but that's going to be pretty expensive. So once you know your KW number and your energy number, I call this know your environment. So now you're going to need to know, if I need X number of kilowatt hours per day, in terms of storage, I've got to know my environment to know how many peaks on hours am I getting? Again, winter peak or summer peak. So how many peaks on hours am I getting? Divide that into your kWh number. Now you're going to need to know, how many kW of array are you going to need to be able to charge the batteries up to provide the energy to power the loads. So dramatic oversimplification. That's why Brad's here. He's my personal Sherpa through the wilderness of energy storage. And I'm going to turn this next slide over to him on a little more detail on battery sizing for off-grid.
Thank you, Josh. Good morning. So in off-grid systems, there's some sort of basic battery sizing parameters that you need to keep in mind. If your charging source is solar, it's intermittent, get cloudy days. So it may not be just that night that you want storage for. It may be for a few days worth of backup. And so in the industry, this was called days of autonomy. How many days, from a fully charged batteries, will the batteries actually carry your loads? And these days, I think generally you're looking at 2 or 3 days of autonomy on a battery bank for an off-grid system. This is assuming that you have some backup generator, because we obviously get more than 2 or 3 days of cloudy weather in many parts of the country. Back when PV was expensive and batteries were relatively not as expensive as the solar, we would try to size the solar just barely enough, and then we would need 5 or 7 days or more of battery autonomy. But these days we're doing a lot more with less, and generally only 2 or 3 days of autonomy is about all most people are going to be willing to pay for, and it's going to be the most economical. And it's just, you're going to need a backup generator for those extended cloudy periods. For those who are trying to do without a backup generator, it certainly doesn't hurt to have more days of autonomy on your battery bank. It just costs more. And it also depends on what part of the country you're in. In some parts of the country, you're you may not get that many cloudy days. You may be able to do with less batteries. Certainly in where I am here in Olympia, Washington, if we were to try to do a system without any backup power, we would be looking at 28 days of battery autonomy or something like that. So that doesn't work so well up here. You can get by with 1 day of battery autonomy. Just have a battery that's basically enough to get you through the night. But what that means is that you're going to be using a generator whenever you have a particularly cloudy day. And some people are okay with that. It can be a little hard on your battery to do that. You're going to be cycling it deeper and heavier and charging it faster and the like. And there may be some batteries that can take that these days. There is a possibility that you could actually size the solar array so that even on a cloudy day, you get enough energy to charge your batteries and run your loads. And then 1 day of battery would be adequate enough to get you through the night. It's depending on where you are, it can be a lot of solar. And also there's not any very good tools for actually figuring out how effective this is. Some of the models I've run indicate that it's quite doable, but there are always a few days that don't work very well. Okay, so the first thing, as Josh said earlier, one of the things if you're designing a system that you need to do, and I think we can look at the next slide here, is determine what your loads are for the system. And this might be a little bit small to see, but basically what you're doing here is listing your loads, how many watts they take and how many hours a day you're likely to run them, and broken down by season, of course, because generally there's a lot less sun in the winter. Sometimes your loads are larger in the winter, although in the south part of the country, maybe the summer loads might even be larger. So you have to look at it seasonally also. And as Josh said, there's, when you're looking at the maximum peak amount of power that you want to run, how many appliances all at the same time, you want to look at which ones are actually likely to be run at the same time rather than just adding them all up and ending up with an inverter that's too large. Things like you're not going to be running air conditioning and heating at the same time, obviously. Whereas your septic pump, your well pump, and your dishwasher may very well all be running at the same time. You may not be running a hair dryer and microwave at the same time, although it's potentially possible. Generally, when somebody's living off grid, hopefully they can keep in mind, in their daily use, maybe not to turn everything all on at the same time. But that's really only has to do with inverter sizing. With battery sizing, excuse me, you're really looking at energy use, how many hours a day of how many loads are you really trying to support.
Mm-hmm. Yeah. Thanks, Brad. Great kind of walk through off-grid and the loads analysis sheet. Now, this is the same kind of sheet we would generally use for, in theory, sizing battery backup, right?
Right. Battery backup is a little more straightforward. Basically, you just need enough battery capacity to power your loads for however long you want them to power the loads during a power out and a utility outage. So it's more of a simple calculation. The harder part of it is to figure out what loads do you want to have backed up, because batteries are fairly expensive. You do have to look and see, maybe you don't want to back up your air conditioning or your heating or your well pump if you have enough water storage to do without it. Maybe you just want some, lights and TV and computer, internet, security system, garage door. So you do actually have to work with your customer to figure out what loads are they willing to pay to have backed up. And for how long. Some people very rarely get outages more than 4 hours. And so that's really all the backup you need. If they have a generator that kicks in, maybe they don't need more than a few minutes of backup power. But if it's connected to a solar system, generally people want to rely on that for at least some number of hours. And some people even want, that system to run their house autonomously in the case of an extended outage, maybe for a week or more, in which case you're sort of sizing the system as though it's off grid, although maybe not with all of their household loads, maybe just with a selected number of loads. Sometimes, if you're looking at just a short backup time, the battery is going to be somewhat smaller than what you would have for an off-grid system. And you do need to be aware of the battery being able to absorb the solar charge that it's going to be exposed to. Not all batteries can take, whatever charge you push on them. Sometimes it will damage them if you push them too hard with too much charging, and may overheat them and damage them.
Yeah, that's a great point there. We're not just sizing to backup loads for backup durations, which can be really small. You've also got to take into account the charge amps there, and if you are AC coupled, those charge amps can be pretty high, right, Brad?
Yeah, they can be, or even DC coupled. If your a solar array is sized to offset your entire household usage, but you only have a little bit of backup because you have selected backup loads, those batteries may be exposed to the entire solar array charging current, although it is possible to also break that array into parts so that only part of it is active during a backup situation.
Mm-hmm. So to kind of put a bow on this and move forward, I think you made a couple comments here that are very pertinent. That I guess the engineering or the math is not necessarily difficult in sizing the loads and figuring out the average duration we've got to plan around, but the soft side of it can be a little trickier. And you touched on that when you said, working with the customer and figuring out what loads do they want to back up. I've heard stories from installers who get caught in this kind of, perpetual cycle of, Mr. Customer, what do you want to back up? Well, what does it cost? Well, what do you want to back up? Well, how much? And you just kind of keep going. So I've seen a couple installers who approach this at, kind of pre-site survey by saying, backup's easy. It's very capable. Typically, we can back up, 2 to 3 or 3 to 4 circuits in your home for 2 to 3 hours. Now, when I come by and we do our site survey and we sign our contract, that's when we'll talk specifically about what you'd like to back up and how many backup minutes or hours this is going to equate to. Not that you want to necessarily kick the can down the road, but you want to make sure you're not doing all this via email or phone and kind of doing analysis paralysis. You got to get to a point where, hey, generally speaking, we're in this kind of frame of reference and what we can back up. Let's get more specific when we talk in person, and I'll be able to give you a detailed number. So that's backup. We've gone through off-grid, we've gone through backup sizing. We'll speak a little bit more, later in some specific chemistries, but I really wanted to take some time now to transition to some of the, blossoming applications we're seeing in solar plus storage, which is going to be everything around self-supply, self-consumption. And we've intentionally left a couple, descriptions and definitions out because there's so much overlap in vocabulary on these applications where, one manufacturer or one manufacturer will call it one thing, one manufacturer will call it another. You hear people talk about self-consumption, self-supply, load shaving, all related. I guess my takeaway here is we've got to be very specific about what we're trying to do. And that's the reason for this slide. So, I touch on this, frequently on this, in this medium doing these webinars about what's the job to be done? What are you trying to do? And I keep coming back to this point that customers, your customers, my customers, people at restaurants, you name it, they're not looking for numbers on a data sheet. If you go to a restaurant, you're not looking for a prescribed amount of calories and a certain, caloric intake. You're looking for a meal. You're looking that when you leave that restaurant, you are satisfied and no longer full, and hopefully with a good experience and great taste and all those things. So the image I found here was, customers, for the most part, they're not buying a drill. They're not buying, 1.2 kWh 18-volt lithium packs. Like, they want to be able to make holes. Ipso facto, they buy a drill. And I think that's what we've got to keep in mind when we're doing all this. Let's keep the jargon kind of, internal to this industry. And when we work with customers, it's got to be around savings. It's got to be around kind of making the application suit their home and their tariffs. So that said, let's not look at all self-consumption the same. Let's be very prescriptive and targeted about what the customer is trying to achieve. And this could be a couple different things, right? Load shifting or load shaving for TOU. So we're seeing more and more utilities move to time of use rates. And if the delta between peak and off peak is high enough, then customers are a great candidate for the self-supply version of self-consumption. I put in here demand charges. We're definitely hearing about, I believe it's SRP in Arizona that has residential demand charges. So for those that, are fortunate enough not to have to worry about those, basically, the utilities rolled out similar program to what they've pushed out in commercial, which is there's an energy component to your bill where you're assessed a fee per kilowatt hour. And then you've got a demand component of your bill. And what the utility does is they look through an entire month's worth of meter interval data, and they look for the highest, either the highest visible or the highest implied KW number during that month. And they charge you a fee per KW. So basically what they're doing is, trying to assess a charge to you based on the peak KW number that you pulled that month, assuming that, I think basically their argument is, you used a peak of 15 kW, and we've got to charge you for that because we've got all of this infrastructure to support peaky loads. So we really appreciate that you pulled almost no power and you've got a really low kWh number, but there was that one day where your system wasn't working and your air conditioner was on and your peak was 15 kW. So we're going to charge you for that the whole month. And we've definitely seen it for commercial customers who say, I'm getting killed on my demand charges. I've done LED lighting. I've optimized my HVAC system. I've got occupant sensors. Like, I'm doing all these things to reduce my consumption, but I'm still getting killed on the demand portion. So we've definitely got applications for that. The sizing is a little different, and we'll go through that. And the last thing I threw in here, it's not a specific application on its own, but typically when we're talking about these solutions for residential customers, you got to think, is backup going to be needed? And it's going to add cost and complexity on the BOS side. You're going to have to think about things like critical load panels and islanding, but definitely a consideration, and can drive some different sizing as well. So just wanted to put this out here as kind of frame of reference. Let's keep the kind of customer's perspective in mind about what are we actually trying to achieve and how is that going to drive our sizing one way or the other. So battery sizing, self-supply. What do you think, Brad?
Okay. Well, self-supply is a little different than, it's a similar concept to off-grid, but it's grid tied and you're serving a different purpose. You're trying to just even out the solar over the day so that during the evening when you're using power and there's no solar available, you can use the solar power that you saved over the day to use it in the other parts of the evening and night. And for this type of use, you really are generally sizing the battery just for the single day cycle at the appropriate depth of discharge. And it's going to make a difference what the load profile is of the site that you're designing this for. You know, if the loads are mostly during the day, the solar may be a good match for them. If the loads are more typically residential loads where the majority of the load is in the evening or in the early morning, then you do need to size the battery to handle the loads during those periods when there's not so much sun, especially if the utility is not allowing you to bank any power from the sun in the middle of the day, or the time of use is making it not economical to do so. So detailed time of use data is very helpful for this. And generally, the utility would be able to supply that data so that you can take a look at what amount of energy you know, the site has been using during the periods of time when you need the battery energy storage. If you have a very highly variable load profile, it might be a little harder, but generally you can come up with something that's going to work for them. And of course, if the customer also wants backup power, you may need to have a little extra capacity in your battery bank to handle that backup power, even if they you know, don't need it necessarily for the self-supply. And people do put a value on being able to use their solar system and their battery bank when the utility power goes down. But obviously, a large aspect of this is the economics of the system, and oversizing the battery, of course, will negatively affect the economics of this. So you do need to keep the battery size to only what is needed for doing the job.
Yep. I'd say it's also going to be critically important for the installer or the designer to really know what's the tariff in that region. If you are looking at this application to try to mitigate the effects of time of use, you got to make absolutely sure you've got the right, you're looking at the right information in terms of what's the peak rate, what's the off-peak rate, what are the times of day when those are in place. And there's been, we've seen a lot of movement on that the last 6 months in some hotbed markets like San Diego, where they've moved that peak, later in the day, knowing that net metered grid tie solar is so popular. They've moved that peak from, I think it was 1 to 7, and it's now 4 to 9. So I guess, bigger opportunity for savings via self-consumption, but you're going to need to size appropriately because you're going to have to cover a few more hours into the evening to be able to do that. Brad, I really liked your point here about extra capacity may be included for backup power. I've seen a couple solutions where customer can kind of program in either different modes, or they can, if the primary function is self-supply, they can leave a reserve in the battery for backup. Just wanted to point that out that most of these systems can do both, but the devil is in the details, and I guess any of the equipment we're working with can do almost anything. The trick is going to be how do you program it, and what decisions do you make it make based on what inputs. That's really kind of 90% of the job, is making sure you've got the right inputs, that you've programmed it to do it the right things. Not to downplay the work of actually doing the installation, but I've seen many installations derailed because the work was done properly and things were wired properly, but they missed a couple critical steps on the commissioning and the programming. So we're going to move forward, and we're going to talk about battery sizing for peak load shaving. So this is that application I was discussing where we're really trying to mitigate demand charges. And the work that's going to need to go into this to do the sizing and make sure that you're putting the right loads, that you're shifting and shaving the right loads is really the proof in the pudding, right, Brad?
Yeah, you have to really have a pretty good handle on what the demand charge loads are and arrange your system so that those can be mitigated with some energy storage. And it's often not for very long periods of time that you get these high power draws. So sometimes the battery has to be able to handle those extra fast and high levels of discharge. And it's also possible to do both self-supply, self-consumption, and do the demand charge mitigation with the same system. There are settings in a lot of the inverters that you can use to do both functions.
Mm-hmm.
But you do need to keep in mind that the battery does need to maybe be capable of a little bit faster discharge sometimes for this.
Yeah, and in thinking about this and how we explain this to customers, when we're doing our homework and we're metering loads, we're trying to find some really peaky loads that to make this cost effective can drive a high kW number, but maybe don't have a great energy usage through the day. So typically we're thinking about rotating assemblies, motors, pumps, compressors, etc., that when they turn on are going to draw a large amount of current, but maybe not a lot of power through the day. So provided we pick the right battery, that we can size it for high current discharge, maybe a couple cycles through a day, but that we're not having to put a ton of amp hours towards the solution because it's not a high duty cycle load. So in working with customers on this, we've advised them to, when they're doing the size, when they're doing the metering and gathering all the inputs, look for loads that have high turn on current, not being used continuously, but kind of peaky loads that are driving that peak kW number. And as you said there, Brad, knowing that you're probably going to need a battery technology that can support high current discharge, that is not going to have issue with potentially multiple cycles a day, is critical. And the metering and monitoring loads. Sorry, go ahead, Brad.
Yeah, fortunately, most of the batteries that we are looking at, the sealed lead batteries and the lithium batteries certainly can handle a fairly large load over a short period of time. I think in a residential situation, probably a really typical load would be a well pump. That may just really peak your kilowatt load on there. But if you can handle that with your self-consumption system, it'll shave that peak load off. And I know that it's only likely to run for 10 minutes. So most batteries can handle that short duration of high discharge.
Mm-hmm. So I think this is a great segue to our next slide, Brad, where we talk about trade-offs between amp hours and depth of discharge, and how do you think about both when we go through the sizing exercise? Right.
Well, there's sort of more into the details of choosing a battery and sizing it. Certainly, some batteries are more amenable to being discharged their whole capacity. Other batteries are not. You may be familiar with all the lead acid type batteries, whether they're sealed or flooded or whatever, really don't like to be discharged their whole capacity. They last much longer if they're only discharged half as much. and actually will last quite a bit longer if they're discharged even less than that. Now, for an off-grid system, 2 or 3 days of autonomy, you're not really cycling that battery more than 20 or 30% per day, and they should last a pretty good long time, depending on which type. So you are looking at balancing the depth of discharge with the cost of the battery. Now, for a backup system, your number of cycles in a backup system is generally fairly small. You're only looking at a dozen cycles per year probably. And so even with a lead battery, an 80% depth of discharge is really not out of line at all for backup systems, and that's generally what's used for that capacity. For self-consumption, you're cycling it daily. You probably don't want to go more than 50% depth of discharge daily. Going to 30% depth of discharge would certainly increase the lifetime of the battery, but on the other hand, it's going to cost more. So you have to find a balance there. Lithium batteries are a little different. They can be discharged and are generally made to last 10 years, with a daily discharge of 80 to 90% or more. Again, they may last longer if you discharge them less than that, 80% or something. Of course, for off-grid, that would be, again, you're in that problem where you're having to run your backup energy source more often if you have that small amount of backup.
Mm-hmm. Yeah, all good considerations there. I think that the only other call out I would make here is to say that I think we're seeing data sheets on lithium-ion batteries are a lot more commonly sized kWh, and the warranties and the manuals are starting to be geared more towards kWh or MWh throughput rather than an amp hours and a number of cycles. So, will cause you to break out your calculator and think about, kind of wattage in, wattage out, and less so around, how many cycles am I going to get out of this? I think, again, because lithium batteries can cycle up to 95% daily, much more tolerant of being at a partial state of charge, and the applications are more geared towards multiple cycles and less so around, one consistent profile every day where you're charging them down to kind of the same rate every day. Much more geared around, self-supply, self-consumption, where we maybe don't know what the discharge is going to be that day. We know that the battery is available. Much more like that than it would be in an off-grid scenario where, you've got a pretty good idea of what you're going to use. What your daily needs and your daily kind of rhythms are going to be. So next thing we want to talk about.
Yeah, for self-consumption, you're going to want to have some capacity in that battery for the solar to charge, and so you really don't want it to be fully charged all the time. Ideally, you'd want it fully charged just before you start using it, but not necessarily. And so you do want a battery that can handle that. Whereas off-grid systems, generally your solar is going to be more than adequate to fully recharge that battery on a daily basis, or at least every few days. And so that does have an effect on what kind of battery you want to have. So the formula is fairly simple for going from amp hours, which is generally what you're going to see for lead acid batteries, to kilowatt hours, which is generally what you'll see with lithium batteries. And I've gotten to the point where I just size all systems with kilowatt hours now, and then do a different calculation later to figure out, what amp hour size lead battery I need. But to go from amp hours to kilowatt hours is really pretty simple. Amp hours times volts equals watt hours, and kilowatt hours is just 1,000 of those. So divide by 1,000, you've got kilowatt hours. That's as simple as that formula is. Now, usable kilowatt hours, of course, you then have to take into account the battery depth of discharge that you want, and also the inverter efficiency, which is often forgotten Inverters are not 100% efficient. In general use, I use 87% efficiency for the better inverters that we sell. And of course, you have to size the battery that much larger to compensate for the inefficiency of the inverters to power the loads that you want to power. And also, at least in lead type batteries, the capacity varies with the rate of discharge. You can discharge a battery in 1 hour, but that total capacity is going to be considerably less than if you discharge it in 10 hours, which is considerably less than if you discharge it over a period of 100 hours. So you have to sort of get an idea of what rate you're going to be discharging that battery, and using that capacity of the battery, not some different lower or higher capacity. Lithium batteries tend to be able to push out the power at high rates or low rates, and they're much less affected by the rate of discharge as far as their total capacity. And residential systems, for self-supply, you're looking at a daily rate generally, so 20 hours. Although if most of the loads are concentrated within 8 hours, you may be wanting to use the 8-hour rate for those. And when you're looking at designing a system, particularly with lead type batteries, any of them, best practice is not to have more than 3 parallel strings in order to get that capacity. The battery has a certain capacity. You have to put them in series to get the voltage you need for the system, and then put them in parallel to get higher capacity. 1 string is ideal, just because the more parallel strings you have, the more chance there is for imbalance between the cells. But there is a little trick that if you're retrofitting a 24-volt system, if you use 2 strings, you can put all those in series later and change this to a 48-volt system, which I've known a number of people have. They want to upgrade their battery now and upgrade their inverter later, mostly for off-grid systems. Lithium batteries are different. Lithium batteries tend to come in blocks that are at the voltage that you're using, 48-volt block, and then you can parallel those. They have internal battery management systems that keeps the balance between the cells, and you can go up to quite a number of parallel strings. I mean, some people are building megawatt-hour battery banks and containers, and with little teeny cells, and they're keeping them all balanced, and there's just thousands and thousands of them in parallel. So that works for those, just not for lead batteries.
You will, of course, need some paralleling equipment for any of those scenarios, right, Brad? I think a little more straightforward on the 2 to 3 strings of 24 or 48-volt strings. But on the lithium front, when we hear from manufacturers that say, the BMS can tolerate virtually unlimited paralleling, we've still got the consideration of how do you parallel that power and get it back to the inverter or the charge controller.
It's sort of like a larger version of a solar array. You've got a whole bunch of parallel circuits, and so you're going to have combiners, and often requiring a fuse or a circuit breaker on each parallel block.
Mm-hmm. We touched real briefly a few slides ago on the need to really take the charge and discharge rates into account, and I think you certainly do a much better job of articulating this than I can.
Well, yeah, battery can only take a certain amount of current before it gets damaged or starts venting gas or overheats. And that is a consideration, particularly not so much for off-grid, because generally the battery is plenty big enough for that. But for backup systems, particularly self-consumption systems to some extent, you do have to watch the sizing of the battery. And different batteries will take different maximum charge currents, and even different lead batteries can take different amounts of charge current. It's not consistent at all. There's different constructions of batteries. Some with thinner plates have much lower internal resistance and take considerably higher charge currents than other ones. There is some correlation between higher charge current and being a less deep cycle battery. Deep cycle batteries having thicker plates and being less able to absorb a high current charge. And of course, lithium batteries are generally known to take very high charge rates. Generally not an issue there. Unfortunately, most of the inverters and charge controllers we have can be set to charge only at a certain rate, but if you're grid tied, you don't want to be limiting the amount of energy that you send into the grid tie system. And separating those two has not really been part of what any of the manufacturers have done to date. So you do have to look at this parameter, and size the battery such that it will absorb the full charge of the solar array, particularly in a backup system. And it's something that gets overlooked quite often, because somebody says, well, I want a 10 kilowatt solar array, grid tied, but I only need, 5 kilowatt hours of backup battery. Well, that 5 kilowatt hours of battery is probably not going to be able to absorb 10 kilowatts of solar array charging it. So you have to either get a battery that can take a higher charge rate, or you have to partition the solar array so that only part of it is actually charging the battery when you have a power outage. When it's grid tied in a backup system, a purely backup system, when the system is grid tied, the battery is just going to be sitting at full charge, and it's not an issue. It's only when the power goes off, utility goes off, and you're running the system off grid that this becomes an issue. With self-supply, of course, you are looking at matching the battery capacity to the solar array capacity as far as the rate of charge.
Yeah, again, because you want to be able to absorb that full, the full wattage coming from the array, right?
Yeah, you want to be able to absorb all of it, so that you can utilize it later, and you want to be able to absorb it and at a rate so that it doesn't damage the battery.
Mm-hmm.
And of course, it works the other way too. If you have peak loads, you need to have a battery that's able to supply that load, over a short period of time. If you have a peak load.
Yeah, if your application is peak load shaving or backup, right? With self-consumption, you're a little less concerned about that.
Right.
Yep. We get a lot of questions on temperature and how that plays into battery selection and battery sizing, right?
Right. Yes, it is definitely a consideration. Batteries are a chemical reactor, and they like to run at a certain temperature. And the manufacturers have to optimize all this chemistry and the construction of the battery for a certain temperature. And of course, the most common temperature is room temperature, and so that's generally where they're optimized. You can get batteries that are optimized for higher temperature or lower temperature, but they're fairly uncommon, and of course have other issues if you do that. So generally, you've got just an issue with capacity. When they're colder, your capacity is not going to be as great. Your discharge current is not going to be as great. And then there's also hard limits on temperature. If you discharge a lead battery and then take it below freezing, it will freeze inside. The water part of it will freeze inside, which damages the battery, regardless of what any marketing hype tells you. I have seen it virtually always destroys the battery if you freeze it. Some say that it will withstand that, but maybe only in a laboratory. So that's if you keep the battery fairly charged, the lead battery will go way down, minus 40 degrees if it's fully charged. So It's just a matter of designing the system so that you don't ever discharge the battery too far if it's going to be really, really cold. But a lead battery tends to have so little capacity when you get too cold that the system stops working anyway. And then there are low temperature limits on the lithium batteries that are fairly hard limits. If you try to charge most of the lithium batteries at below freezing, it affects the chemistry in a way where it plates the lithium out on one of the active materials and damages the battery permanently. So lithium batteries really cannot be run at a lower temperature than freezing. Although some of them actually have heaters in them to prevent that, but of course that cuts into your efficiency and your economics. High temperature limits, lead acid batteries lose half of their life for every 13 degrees Fahrenheit above their optimum operating temperature. That's pretty severe. And some of you may have seen that, in where the batteries are really hot, they don't last very long. Lithium batteries are rated for up to a certain temperature. I don't know exactly how much life they lose at higher temperatures. They're best if they're kept at a fairly moderate temperature. And remember that batteries are fairly massive items, and so the battery temperature itself does not cycle as much as your ambient temperature. So if you're at 120 during the day and 80 at night, it's going to be an average temperature of 100 degrees, and the battery is not going to vary more than a few degrees per day. So you're not looking at the peak temperatures, you're looking at the average temperature of where that battery is. And you may be able to do things like a well-insulated shed that's earth coupled, in a hot climate, in a cold climate, maybe within the conditioned space or basement, to keep the batteries at a more steady, even temperature tends to work best.
So Brad, on the coming from the lead acid side of the business, we've got insulated boxes that are available. And I like the image of the array here with 3 inches of snow on it. In the instance, customer absolutely has to have lithium ion, and it's a cold weather environment without a conditioned space. Sounds like the options are what you've laid out there with a shed with some, I think you used the term ground coupling, an insulated box, maybe a heater. But yeah, definitely want to call out the temperature component here. We get a lot of requests on the LG Chem product, specifically around, can I install it outdoors in northern Canada? And I usually defer those questions back to you, Brad, but the first question is like, the first pushback to the customer is, geez, why would you want to? Is there any other option available? If it's a question of, oh, well, it's easier if I put it outside because then I can get to it. I usually counsel folks, hey, this is cutting edge technology. These are very expensive, kind of guard them with your life. And definitely you did a good job here speaking to the chemistry, the chemical reasons for wanting to keep these within the right temperature range, as well as it's you read through the manuals in these things, and they're the lithium guys are very specific on permitted and recommended operating ranges.
Right. One of those operating ranges is altitude also. You have to look at the maximum altitude rating on some of the batteries because there are some hard limits there, and they're not that high altitude.
And that's going to drive the dielectric rating, is that right?
I am not sure if it's the dielectric issue or a cooling issue, or both. As the air gets thinner, as you get up in altitude, the dielectric strength of the air is reduced so that you can get arcing more easily between terminals. Also, of course, thinner air has less capability for cooling, and so it's easier to overheat things at the higher altitude.
Yeah. So this is a slide you put together for us, Brad, with just some real simple sample calculations. If you want to walk through that, I've got, I think, 2 more slides, and then we'll have some time for some questions.
Okay. So I just took a sample load of watt hours per day and a calculation to figure out how you would size a battery bank for this, particularly for an off-grid system, but it could be used for other systems. So you've got watt hours per day, you've got the number of days you want that to go. That could be hours also. The depth of discharge you want to take the batteries down to, and of course temperature derate. And so you're just multiplying the load by the time that you want it to run, and then dividing it by the derates of the depth of discharge and the temperature, and it comes up with your gross battery size. You know, for a lead acid battery, you would need to change that to amp hours, which is sort of the opposite of the formula that I gave earlier, where you're taking the watt hours and dividing it by the voltage, and it gives you the amp hours. In a lithium battery, you can just start with that watt hour size and just go with that. You know, change it to kilowatt hours. And of course, don't forget that your inverter is not 100% efficient, so you have to put that in the calculation also, which I am not showing here.
Gotcha. Okay, thanks, Brad. I wanted to show, just provide some screenshots and some links to 2 of the more popular tools we've seen for storage sizing. Homer Pro on the left is a fully built out software platform, really geared towards off-grid and microgrids. Can do some really great modeling of solar, wind, generator, and really dial in, you know, the sizing around all those other components that you're going to need. Energy Toolbase on the right is much more suited towards, I'd say, backup, self-consumption, you know, grid interactions. So the snapshots are going to be really hard to see there, but we've gone through a couple demos on this platform, and it's really strong. Allows you to pull in interval data, allows you to pull up rate schedules and model out, okay, for this application, what are my best system parameters? And then on the flip side, for this system, do I want to coach the customer to go for this optional utility program, or maybe this one? You know, you can model up a home with a system and figure out, is it best for this guy to stay on a tiered rate? Should I recommend that he move to a time of use rate? What are his savings going to be under those different scenarios? So some really powerful stuff. Heard great things about both of these from customers. Yeah, we don't sell either of those products. I don't get a kickback or, you know, a referral bonus. Just wanted to provide you guys with the materials there and say that you know, both of these are powerful tools and can help you put together proposals and really speak to what's the customer going to save, which at the end of the day is a really strong consideration anytime you're looking at selling one of these systems. So I want to make sure you guys have that information. At this point, I think we're a little over schedule, but we do have a few minutes here for some questions, if any have been sent in. So Caitlin, we'll turn it over to you.
All right, thank you both. That was a lot of good information. I'd like to go ahead and start off our question and answer session now. So if you have any questions, go ahead and submit those to the question pane located on your control panel, and we will try to answer as many as possible. You can always exit the webinar at any time during or following the question and answer session. A survey will pop up in a new window once the webinar has ended. If you can go ahead and give us your feedback on the survey, I will send the presentation over to you. So we'll go ahead and start off the question and answer from Sal. He's wondering, how do we size the battery system with demand charges?
Yeah,
well, that's a good question.
Yeah. It's you want to take this one, Brad, or you want me to muddle through it? Okay. So
I'll let you start.
Okay, fair enough. So this is going to sound like me punting, but it's basically going to say it depends. You know, you've really got to go out and look around the customer's site, Try to figure out, in your opinion, as a designer installer, what are the loads that you think are driving that peak number? If it's, quote unquote base load, if it's an office and it's lights and computers, you're not going to put those things on a storage system and try to island them and remove peaks, because those aren't peaky loads. Those are, long duration loads. If there is, if there's HVAC equipment with real high turn-on loads, that could be something to investigate. But typically, that's going to come with a high enough kWh number that it's not going to be cost effective to put that behind a critical loads panel and try to island it from the rest of your panel, which is really the application that we're talking about here, where you're going to put in an inverter charger system that's going to go between the main panel and I'd say a sub panel. I won't call it a critical loads panel because it's not backup. It's basically the opposite. You're trying to island it from the grid when you want it to run and the grid is active. The thinking there being, if I'm capable of islanding this load, I can keep that surge kW number from hitting my meter, and I can keep my demand charges lower. So you're going to have to meter, a lot of different branch circuits and figure out, which ones are peaky, which ones can I island relatively easily that have a high peak number, a low energy number. And it's, I won't say it's trial and error, but, you're going to need to